Okay, thank you, Raghav. Welcome to lecture 21. In the last lecture, we defined an object, collection of sets, in fact, what we called as matroids. Okay, so a quick recap of the definition. A matroid comes with a finite set, which we call as a ground set. So this is called the ground set. So a ground set along with the collection of subsets, which we call as independent sets, with the following properties. Empty set should be independent. And it should be closed under subsets. So with this property we call as closure under subsets. That is, if A is independent and B is a subset of A, then B should be necessarily independent. The third is the most important property. This is generally referred to as exchange axiom or exchange property. Or in general, this is called as Matroid exchange axiom. So here, if you have two independent sets and one is larger than the other, then the smaller one can be grown by adding one element from the larger one. That is, formally, if cardinality of A is less than cardinality of B, there is an element in B but not in A, such that if you add this element to A, the resulting set still remains independent. Okay. So the last lecture we defined one matroid which is based on graphs. So let's just quickly look at it. So today we'll be proving the property of proving that this object that we defined from a graph is in fact a matroid. So take any undirected graph. Now I'm going to define a matroid-like structure, and I'm meant to prove that it is a matroid, of course. So the collection of edges, that is the set of all edges, is the ground set. Now independent set is a subset of edges. So a subset of edges is independent if the corresponding graph does not contain any cycle. That is, these edges do not form a cycle. So all acyclic subgraphs. Okay. So this was the example that we saw in the last lecture. Okay. So we verified that for this example, the three properties hold. In fact, the exchange property you can verify by brute force here, looking at all relevant pairs. Okay. So here the only non-independent set is something that contains the cycle. Okay. So something that contains the edges 1, 2, 3 will not be independent. That is 1, 2, 3 as well as 1, 2, 3, 4. These are the two sets which are not independent. Everything else is independent here. So in fact, it turns out that these collection of sets, so just for a moment, so what are these sets? So collection of edges, which does not contain any cycle.
Forest.
Yeah. Hello.
Yes, sir.
Yeah. Go ahead.
It will be forest, right?
Yeah. So it is called forest, right? A collection of trees.
Yes.
Not necessarily connected. Okay. If the graph, to begin with, the graph is connected, then what are the maximal independent sets? When I say maximal, that is, it should not be contained in any other independent set. So here, for example, these three are the maximal independent sets: 1, 2, 4, 1, 3, 4, 2, 3, 4. So if the graph is connected, it has to be a tree, right? It's a spanning tree of the graph. Yeah. So this graph, this set has this special property that maximal independent sets are trees. Suppose G be connected. Maximal elements in I are spanning trees. Okay, so that's an important aspect here. So yeah, so now it remains to prove that the set indeed is a matroid. So we'll verify. So this matroid is called graphic matroid, or some literature also calls it as cyclic. So graphic matroid, or also as a cyclic matroid. So I'll tell you why it is called cyclic later. Okay, it has close connection to cycles. Okay. So let's verify I1. So I1 basically says empty set should be independent, which by definition is, right? So you are looking at subsets of edges which does not contain a cycle, which do not contain a cycle. That means empty set certainly does not contain, right? So empty set is true, verified. I mean, empty set is independent, so I1 is true. So how about I2? So if A has no cycle, then any B in A also does not have any cycle. By removing edges, you will not be introducing cycle, right? So if you have a subset of edges which does not contain any cycle, now any subset of it cannot have cycle. So it's also independent. So I2 is also verified. I1 as well as I2 are verified. Now only non-trivial part is I3. Sorry. So let's just state I3 again in our language. What is it we want? So for any AB which are independent, if cardinality of A is less than cardinality of B, okay, cardinality of A is less than cardinality of B, then what is it we want? There should be an edge in B such a way that if you add it, this is still cyclic, or A union edge is still a forest. Okay. In other words, A union should still be independent.
Sir, your
Hello,
voice
sir.
is not clear.
Your voice is breaking.
Your voice is breaking.
Oh. Let me check. Is it better now? Hello, is
No,
it
sir.
better? No, okay, so just give me a second, okay? So I'll connect to some other network, okay? So in a second. Okay. Yeah, so is it better now?
Yes.
sir.
Yes, sir.
Okay, okay, good. Okay, yeah. Okay, so in the language of this set, all we wanted is if you have two forests, one has larger number of edges, then we should be able to move at least one edge from the larger forest to the smaller forest so that the smaller set still remains a forest. Okay, so that's exactly what I3 is. So this is what we are going to verify now. So for this, let's demonstrate it with an example. Then we'll get to the proof. Okay. So suppose this is our graph. Okay. So here I have two forests. So the smaller forest is marked as green. Okay. So the green dashed edges are they're part of A. Okay. That is this edge, this edge, this edge, and this path of length 2. Okay. Now B is red colored. So it is this 3 edge and this path of length 3. Okay. So now what is the number of edges in A? It is 5. Number of edges in B, 6. So let's mark it. So 5 edges and then 6 edges. So now let's look at candidate E that we want. So there are lots of E's here, which are candidates in this example. So if I take, let's say, this as E. Oh, sorry. Yeah. So this as E and add this to A. It still remains a forest, right? So A union E sorry. I hope I am audible. A union E has no cycles. So therefore, A union E is in I. Okay. So how is the general scenario? So in this case, I mean, E need not have been this alone, right? E could have been any other edge, which is not present in A. So this could have been E, this could have been E, this could have been E. So in general, so let's just try to understand why did this work. So let's just try to build something adversarial. Okay. So what would have been the problem? So any edge which is in B, which is not present in A, if I add this to A, if it forms a cycle, then I'm in trouble, right? That's the only bad case, right? See, whenever I take any element from from B, which is not in A, if I add this, this should contain a cycle. If it contains a cycle, then it cannot be independent by our definition. So only way to contradict I3 is by the property that every edge in B which is not in A should form a cycle in A. That means if I add that particular edge, it should form a cycle in A. Okay, so let's just try to build it. Okay, so for that, what I'll so help me building potential counterexample. Of course, there won't be a counterexample because the statement is true. But let's just to play the devil's game, right? Let's just try to understand it. So I'm drawing A. So if you have any suggestion, let me know. Unfortunately, I haven't labeled the vertices. Okay, maybe I'll quickly label vertices. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah. So let's try to beat it. So the idea is you want A and B such a way that any edge in B which is not present in A, if you add it, it should form a cycle. That is what we are going to. So let's choose some A arbitrarily. Okay. So let's use a different color. So I'm going to use this color to indicate A. Okay. Sorry. So okay, so how do I do that? So let's take this, take this, take this. Take this. Okay. And take this. Okay. So this is my A. Okay, I'm just trying to build it. If you have any suggestion, please let me know. Now, what do I want? I want in B, whatever if you add, right, it should create a cycle. Okay. So let's try. So B, what color should I choose? Maybe green. Okay. So B is green here. So I'll take this one. So all those that close a cycle, I'll take this one, these two. I can take this one, 3. Okay. So how many edges do I need in B? One more than A, right? At least one more than A. So A has how many? 2 plus 3, 5. So I'll need 6 edges, right? So now 3 I have got. Maybe let me also go back a bit and I'll put this as an edge here, okay? I don't know how thick it is. Okay, sorry. So all I'm doing is I'm just playing devil's game, okay? I'm just trying to refute I3. We'll come to the formal proof very soon, but let's just try to understand why it should be true. Okay, I'll just added this edge to the original graph just to play our game, okay? So then I'll take this. Oh, sorry. I'll take this. Okay. How many edges are there? 1, 2, 3, 4. Now, is it possible to add any more edge in this graph? So that still we don't have cycle? Maybe the 13, 11 is not an edge in this graph. Suppose that's also an edge, so that I can take it. Okay. Then I add this. Okay, so I have 5. I need one more. So now without creating cycle in B, is it possible to have another edge for B such a way that that edge also creates a cycle in A? So it's clear, right, what I'm trying to do? Yeah, somebody please respond. I'm not sure if I'm audible.
Yes.
Yes. Okay. Okay.
Sir, we can take 113, 12, and 23 in B.
Say it again. I missed the first one. What
Sir,
was that?
113.
113. So you're constructing a completely different example, is it?
No. In that only I am adding the edges to B so that it will form a cycle. So that every edge will.
No, so 113, the moment you add 113, 113 is not in A, right? So 113 will not form a cycle in A, right? We already lost, right? We already lost the game.
Yes,
right?
sir.
So it should form a cycle. So the only way I see is 1388. I can add, which also creates a cycle in A, but it also creates a cycle in B. Another possibility is that, I mean, include that in my graph and then add that edge. Then every other possibility, I find a cycle in B as well. Right? And of course, it's for this example. Maybe you can argue that maybe you should take some other example. But is it clear? For this example, it is not possible.
Yes, sir.
Right? So in other words, if you look at the number of, see, what is a property? So let's just assume that both are connected, okay? I mean, in the sense that, I mean, just to understand, otherwise we'll apply it for each component, that is each tree, okay? So in a tree, so the number of fundamental cycles, right? See, I mean, I'm just giving an intuitive reason, okay? The rigorous argument will come very soon, okay? So let's say tree has graph has n vertices. So number of edges in any spanning tree of it is n minus 1, right? Okay. Now, I mean, n is the size of this set, okay? Size of this set. This is what I'm referring to as n, okay? Now, each of them, so each of these candidate edges that I'm trying to add should be a fundamental cycle. All of you know what is a fundamental cycle, right? If you take a tree and add an edge to it, a new edge to it, it's going to be there is going to be a unique cycle, right? That cycle we are calling it as fundamental cycle. Okay, so these are all fundamental cycles of this blue colored tree. Okay, so but can you, if you want to add one more than the number of edges in this tree, I'm going to create a cycle among these, right? So if I'm restricting to A, that is the set of vertices is the same, I'm not going out of it. If I'm putting edges in B within only those vertices, if I want to exceed the number of edges than A, if it is within, I am going to create a cycle in B because it's going to exceed this number n minus 1. So my only way is I have to span out. Only way for increasing B, having more edge, is I have to span out of this. It could be somewhere else in some other component, or should be an edge outside of this. If there is an edge outside of this, that is set of edges in A, that can be added easily to A, right? So that there is no cycle. Yeah. So this is exactly the reasoning. Okay, we'll give a formal argument now. Yeah, is the reason, intuitive reasoning clear? If I want to have more edges in B, so you can just imagine, I mean, to counter this, all I'm going to do is I take an A and then construct a B such a way that every edge in B, it's either in A or it's creating a cycle. Okay. Now the idea is if you are going to have more edges than in A,
hello sir,
it's not possible unless you create a cycle in B. Yeah.
Sir, am I audible?
Yes, go ahead. Yeah.
Sir, can you explain that n minus 1 part again?
No, I was just saying, so suppose, so you have, so A is a tree, okay? Basically, I mean, it's a tree of subset of vertices. Say that subset of vertices is n minus 1. So in any tree of n vertices, there are exactly n minus 1 edges, right?
Yes, sir.
Right? Now, when I construct B, it should have more than that edge, right?
Yes, sir, because it will contain.
So only way, so what is the property that I need? Either the edge in B is also in A, okay, or it's the edge is such a way that if I add this edge to A, it should create a cycle. They basically should correspond to fundamental cycles, right? Okay. In A.
Yes, sir.
But so the point is, the moment I have more than n minus 1 edges, if the vertex set is going to be the same as that of A, okay, then the problem is if I cannot have more than n minus 1 edges without creating a cycle in B itself, right?
Yes, sir.
So the only possibility for me to add an edge to B is to grow out, because I want more edges. So once the moment I grow out, I can add that to A as well without creating a cycle. Okay.
Okay, sir.
Yeah. So that is the intuition. Yeah. So now we'll make it as a formal argument. Okay. Yeah. So this argument is from the book CLRS. Okay, CLRS book, Introduction to Algorithms. So let's take any two subsets of edges such that cardinality of A is less than cardinality of B, and both are acyclic. That is, G of A and G of B are acyclic. Okay. So the main claim that we are going to prove is we are going to count the number of trees in A as well as number of trees in B. Okay. So the claim is G of A has more trees than B. So there is one small thing that I want to say. So for this example, right, what is the number of trees in A? So this is one tree. This is 1, 2, 3, 4. Okay. But there is a small catch here. Okay. So yeah, when I say this number of trees, I'm not only counting these. I'm also counting there are isolated trees. Okay. Single vertex trees. So this is a tree. This is a tree. These are all isolated vertices. So I'll also be counting these. Okay. Is that clear to everyone? See, the vertices for which there is no edge incident in A, they are also counted as trees. Okay. So the number of trees in A now will be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So number of trees in A, 9. Okay. Number of trees in B. So what's the number of trees in B? Let me use the color red. So this is a tree. This is a tree in B. 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 Okay. So what is it? 1, 2, 3, 4, 5, 6, 7, 8. Number of trees in B is 8. Is that right? I hope I counted it right. Yeah, is it clear when I say number of trees? I'm also looking at the isolated vertices. Each of them is counted as a tree. Okay, that is what I mean when I say tree. Hope there is no question. Okay. Okay. So the claim is the graph induced by A has more trees than graph induced by B. Okay.
Sir, can you count number of trees in B once again?
Yeah. So this is one tree. 1, 2. Okay. Now the isolated vertices 3, 4, 5, 6, 7, 8. Okay. Yeah.
Okay, sir. Fine. Yeah.
Fine. Yeah. Okay. Let's see at once why this proves our property. Okay. So I mean, this is the example. Okay. So I've already done. So I'll skip this. Okay. So yeah, I already counted the number of trees here. Okay. So yeah. So why does this prove immediately? See, the number of trees in A is more than number of trees in B. What does it mean? So let's just see. So let's say T1 to Tk trees in A, W1 to Wt trees in B. What we know is T is less than K. Yeah. So in fact, this picture itself kind of demonstrates it. So if you look at the edges of B, okay, there are more edges and smaller number of trees. What does it mean? There should be at least 2 trees in A. Okay, so in this case, these 2 trees in A that are connected by an edge in B. Okay, so this basically means, so then there is an edge E in B that is between two trees in A. It could be two isolated vertices, or it could be two components. It has to be, right, because the number of edges trees in B is smaller, but it has more edges. If you have more edges, but the number of trees is smaller, so let's take this simple example where say K is 2 and T is 1. Okay, so okay, so maybe here. Okay, so let's say this is it's easier to demonstrate pictorially. Okay, say this is T1 to Tk. Okay, now in B I have at least one less. What does it mean? There has to be an edge in B which connects two of them, right? There has to be an edge in B which connects two of them. Otherwise, how do I get a smaller number of trees, right? See, trees are nothing but connected components. So how do I get smaller number of connected components? I have to connect to two components, right? If I'm going to get smaller number of trees, that means it's the same vertex set. That means there has to be an edge between at least two of them. That is one Ti and Tj. And what does that edge do? Can it create a cycle in A? It's connecting two trees, right? It cannot create a cycle. So this edge cannot create a cycle at all. Is that clear? Because I have smaller number of trees in B, at least two of them will be connected. It could be multiple. It could be more than two. Okay. So in the other example, there are a lot of trees that are connected. This example, there are a lot. Sorry. Yeah. See, these trees. These are all green vertices, right? So these are trees. So these are connected by edges in B. This is again connected by edge in B. Okay. So yeah. So if you just look at this green dots and the green edges, so these are components. Okay. So what we have is, the moment we have lesser number of trees, it has to be that between two trees there is an edge. Not any two trees, some tree. So in this case we have a lot. So this is an edge. So this is a tree, this is a tree in A. This is a tree, this is a tree in A. This is a tree and this is a tree, but this does not, there is no edge. Okay. And this is a tree and this is a tree in A. So we have an edge. Okay. So in this example, there are lots of edges, but what we are guaranteed is at least there is one edge. Okay. Because there are smaller number of components. You can just think of it as components. These are connected components, also counting isolated vertices. Then if you have smaller number of connected components, that means two components in the original, that is A, should be connected by an edge, right? That is all. Okay, so now all that remains is proving the claim. Yeah, so one minute. Is there any question here? I hope I am audible.
Hello.
Yes, sir, you are audible.
Yeah. Good.
Sir, just a question.
Yeah.
Suppose A and B are completely disjoint.
Yeah, then it's perfectly good, right? Yeah.
But this this claim, like not the claim, this statement, there exists an edge in B that is between two trees in A.
Yeah.
Will that be valid?
Yes. So when I say two trees between edge between two trees, I mean so one endpoint is in one tree, the other endpoint is in the other tree. That's all. The whole tree may not be present. See, when I say there is an edge, okay, so this edges in T1 may not be present in B. This edges in T2 may not be present. All we want is an edge across. That is all. which is true, right? Which has to be. If you are going to have a smaller component, that means how do you have a smaller number of sets? Two of the sets might, I mean, they may not be merged completely, but there has to be something between them, right? Otherwise, you cannot have smaller number of sets, right? So you can just imagine these as sets. If you're going to have a smaller number of sets, there should be, you may have to take union, or it may not be union completely, but at least it should be that two of them, that is, yeah, one vertex from here and one vertex from here should be connected. There's no other way possible. It may not be complete merger because the trees will have a completely different structure, but it should be that, I mean, what I mean to say is the following. So if you have a smaller number of sets compared to T1 to Tk, the smaller set will have to somehow have some mingling of the vertices, right? Otherwise, how do you get a smaller set? It is not possible to get a smaller set. So that is all.
Sir, can we go to the diagram?
Yes.
Sir, let us suppose my B is 13.1. Are you talking about this diagram?
Oh, this diagram. Okay. Okay. So this one, this fine.
13.123. 13.123, the top part.
13. Okay. Wait. I'm drawing. Just a minute. My B is 13.123. Yes.
Yeah. And my A is 765.
7. This is
Here,
6, right? Okay. 765. Yeah. This is A. Okay. Sorry.
Yeah.
I should have been a different color. Yeah. This is A. Yeah.
I'm not understanding in this case what that statement, whatever the statement is.
Yeah. So now what are the components? See, what are the trees with respect to A? 1, 2, 3 are trees anyway, right? See, we counted isolated vertices, right? So this is a tree in A, this is a tree in A, this is a tree in A, this is a tree in A. These are all trees in A.
But they are not in A, right?
No. So when I say tree, right? So this is also one of the TIs. Say A. So A is this along with. So when I count, right? How did I count the trees? I counted as all isolated vertices are counted as trees.
Oh, okay. Then
that's
very
the main
good.
thing.
Okay.
Yeah.
Yes, I understand.
That is all. Okay. Yeah, that's a trick there. Okay, so you're not on. I mean, so if I just say the word tree, then this is one tree. Then it's fairly confusing. Also, this claim itself is false. For this claim to hold, I also need to count these as trees. So each isolated vertex is a tree. Okay, that is important. Okay. So let's quickly. Yeah. So this is the argument that I said. So T1 to Tk be the trees in A, and W1 to W2 be the trees in B. Then B must have an edge between two trees in A. Say E is the edge. Okay. So what happened? Okay. Yeah. So this is the statement. Okay. Now all that remains is to prove the claim. Let's prove the claim very quickly. Okay. So claim is a very simple statement. So we just show that the number of trees in the graph induced by A is exactly cardinality of V, that is number of vertices, minus the number of edges in A. So remember that A is an acyclic set. So the number of edges in A is strictly less than number of vertices. So this is a non-negative quantity. Okay. So I mean, the same statement is true for B. I mean, this is for an arbitrary A. So that is number of trees in B should be cardinality of B minus, cardinality of V, that is, let's say N minus cardinality of B. Okay. So does this prove immediately? I mean, does this prove the claim immediately? It does, because cardinality of A is smaller than cardinality of B. So hence the number of trees in A should be more than number of trees in B. Okay. So yeah, so this is a fairly simple argument. So let's consider A for now. Okay. So let's say A is an arbitrary forest, and let's say T1 to Tk are its trees. Okay. So Ei be the number of edges in Ti. Then by definition, total number of edges in A is sum of Ei's, right? So cardinality of A is sum I equal to 1 to K Ei. Okay. So let's say the number of vertices in Ti is Vi. So each Ti is a tree. So number of edges there is number of vertices in that tree minus 1. Okay, so Ei is Vi minus 1. So let me put that down. So then this is equal to summation I equal to 1 to K Vi minus 1. So there is a bracket here. Sorry. So how does this sum to? So let's expand it further. So summation I equal to 1 to K Vi minus K. There are K summands, right? So what we have proved is cardinality of A, that is number of edges in A, is equal to total number of vertices minus the number of trees. That is K is equal to cardinality of B minus cardinality of A. So here the only trick is, so I'm assuming that sum of Vi I equal to 1 to K is V. That is number of vertices. This is number of vertices. So that is the reason why I need to count also the isolated vertices. If I didn't count the isolated vertices, sum of Vi, so in this example itself, sum of Vi, so what is Vi for, let's say A? So this is 3, 2, 2, 2. 3 plus 2 plus 2, that is 7 plus 2, 9, right? But we had 14 vertices, right? So this won't sum to the total number of vertices because we didn't count these isolated vertices. So that's the reason why we need to count isolated vertices for this statement to hold. Otherwise, we will not get this is equal to V. Okay. So therefore, the total number of edges is nothing but total number of vertices in the graph minus this K, where K is the number of trees which is induced by A, including the isolated vertices. So therefore, number of trees is exactly cardinality of V minus A. That's what we needed. So once we have this, by the fact that cardinality of B is more than cardinality of A, we have that number of trees in A is more than number of trees in B, because they are basically cardinality of B minus the number of edges. Okay.
Hello.
Yeah.
Sir, can you define G of A then?
Yeah, I mean it's a graph induced by what I mean. See, I'm just using A itself. So if you just include only edges in A, how does the graph look like? That is it.
Keeping the vertex set same.
Yeah, that is important. Keeping the vertex set same. Yeah, including the whole vertex set. That means that we'll have some isolated vertices too. Yeah.
Sir, can you explain how we have written EI equal to VI minus 1?
Yeah, so EI is a tree, right? So this example, let's see. EI is a tree. So this is EI. It's a tree on how many vertices? So EI was 2. So I mean, EI is the number of edges in a tree. So that is TI is a tree on 3 vertices.
Okay.
Now, so for any graph, right? So if there is if it's a tree on n vertices, the number of edges is n minus 1, right? That's a fact that we have used.
Okay, sir.
Yeah. So maybe I'll just write a clarification here. So here, sorry. Any n vertex tree has n-1 edges. Okay. So Vi is the number of vertices in Ti. It could be 1. I mean, if it is an isolated vertex, then it is 1. So then this contribution is 0, which is true, right? If for an isolated vertex, it has 0 edges. Yeah. Is it clear?
Hello, sir.
Yes.
Sir, can we think of like this initially? How we construct A is like we have V number of vertices, so we have V components. Now, when we join one edge, we get one component less. So as many edges we join, we get that many components less. So it is mod V minus mod A.
Yeah, intuitively, yes, that's correct. Even I think you can also write a formal proof with that idea. Yes. Yeah. Okay. Okay, so that's it.
Hello.
So, yes.
Sir, just can you go to the argument where we said there exists an edge in B such that when you add that A,
This one, right? Yeah.
just can you repeat over this argument?
Yeah, so this basically says, so if T is less than K, right? So how do we, I mean, so maybe, I mean, who was it? Was it Apurva who asked the question previously? Who spoke? I don't remember the name. Yeah, who spoke just before now?
I asked the question now.
No, before you.
Okay.
Your voice I can identify. So, okay, fine. So see, you can just imagine. Okay, so you're just adding edges. Okay, so you're just adding edges of B. So what are the choices that you have? So if you don't want to violate, so the worst possibility is you're adding edges within the vertices in some Ti. Okay, you keep on adding. Okay, so there is, if I draw it here, it will look bad. Okay, I'll draw it here. Okay, say this is T1, T2, etc. TK. So this is probably the best way to explain. Okay, so I'm going to add edges to B. Okay, so my possibilities are add within Ti or across. Okay, so if I keep on adding within Ti, I'm going to have at most K connections, right? I mean K connected components, at least K connected components.
Yes, sir.
But the statement is I will have at least one component less, right?
Okay, fairly then we have to add between the components.
Exactly, that's all. It's basically a pigeonhole principle kind of argument.
Okay, that's
probably this is the best way to imagine it. Yeah. Yeah. Okay. Okay, so I'll skip this portion now. So I'll prove one important property of a matroid. Okay, so that is something very crucial. So start with an arbitrary matroid. Okay. Now a maximal independent set is called a basis of a matroid. Okay, it's just a name. A basis of a matroid is a maximal independent set. So if you have say a connected graph, right? And if you consider the graphic matroid, what are the maximal independent sets there? That is maximum, maximal acyclic subgraphs, spanning trees, right? That's what you said. Yeah. So spanning trees. Okay. Now, if you look at all possible spanning trees, what is their cardinality? They have the same size, right?
n-1.
n-1, right? Yeah. Okay. So a basis, say for example, for a graphic matroid is a spanning tree. And we know that the basis for a graphic matroid, they will all have the same cardinality because spanning trees will have exactly n-1 edges. Okay. Yeah. So now we are going to say that it's in fact a property of any matroid. nothing to do with the graphic Matroid. You take any Matroid, your choice, their basis, that is maximal independent sets, they will all have the same cardinality. That is our main statement. Okay, so that is, so consider any two bases of a Matroid, then cardinality of B1 should be cardinality of B2. Okay. Yeah, any question on the statement? So I'll just give one line proof. Okay, so maybe you can prove it yourselves. I mean, just follows from the axioms. Okay, so proof.
So just before that, the
Yes.
statement maximal independent set in M is equivalent to the statement A is a maximal element in the independent set in M.
Yeah, that is what.
That's fine.
Yeah. So you consider I and look at largest cardinality sets there. They are maximal independent sets. Okay. So now we are saying that they will have the same cardinality. Okay. So suppose cardinality of B1 is not equal to cardinality of B2. So remember that this so since these are natural numbers, they should be comparable. So cardinality of B1 is less than cardinality of B2. Then by I3, there exists a E in B2 minus B1 such that B1 union E is also in I. But B1 is a basis. That is for all A such that B is in A is not in I. That's the definition of maximal independent, right? It should not be contained in any other independent set. Hence, it is maximal. So it is a contradiction. Because we already have B1 union E is independent because of this assumption. Therefore, cardinality of B1 cannot be less than cardinality of B2. Similarly, cardinality of B2 cannot be less than cardinality of B1. So therefore, cardinality of B1 is equal to cardinality of B2. Okay. It's a simple consequence of the exchange axiom. All maximal independent sets will have the same cardinality, which was easy to see in the graphic Matroid case. Okay, so because I mean, particularly when you have a connected graph, if it's a disconnected graph, you can just consider one connected component and focus on it. Okay, then all maximal independent sets which are spanning trees have the same cardinality, which is not just a feature of this graphic Matroids, it is a feature of any Matroid. If you take any Matroid, now you can go back and look at the examples that I have presented. At least I think there was one example or two examples probably. Both of them you can see the maximal sets will have the same cardinality. I think in one example there is only one maximal set, so then there is no question. Okay, so when you have multiple maximal sets, the question arises. But the interesting point is they have the same cardinality. Okay, so it's easier to imagine Matroids pictorially. Okay, so this is always, I mean, whenever you imagine Matroids, this is a picture that you should keep in mind. Let's recall this Hasse diagram that we drew in a discrete maths course. I believe most of you must have seen. Okay, which is basically diagram of the partially ordered set on all subsets of say 1 to n. Okay, so that there are 2 power n subsets. What I do is I draw the full set, that is the full universe at the top 1 to n, the empty set at the bottom. then cardinality 1 sets in one layer, cardinality 2 sets in another layer, and so on, layer by layer. Okay. Now draw an edge between two sets if one is a subset of the other. Okay. So for example, if I have this as 1, 2, this as 1, then I'll put an edge here. Okay. I hope everybody is familiar with this. Okay. So now, if you take a matroid, so matroid, so let's say has ground set 1 to n, then it's a collection of subsets, right? I mark the independent sets in the matroid with green. So these green dots are matroids. Okay. These are part of matroid. Now, if you look at the maximum size, which is the size of a basis, say for the matroid it is k, then my green dots will stop at k. It will not go any further, right? Yeah. So now the matroid property, it says if you start from empty set, if you keep on adding so that you stay within the green dot, no matter what choice you make, okay, you can always reach the top. You can always reach the top layer. You'll never get stuck anywhere. You'll never get stuck at a place where you entered a green dot, but nothing above it is a green dot, unless you are at level k. Okay. Yeah. So this is the intuitive thing. So we'll continue from here in the next lecture. I'm already timed out. Okay. So, okay. Thank you all. Raghav, you can stop the recording.